right, guys, we are on the back side of day 11 notes for unit 5, and number 1 says which function represents exponential decay. So if someone was looking at this just based on the bases alone and knows that the base has to be between 0 and 1, they're going to go ahead and pick choice 3. But just to show you guys what we did on the front side, that in number 3, because that exponent isn't just a t, 1/2 isn't our true base. And so we're going to go ahead and take that 1/2 and raise it to the negative. And we can't just raise it to a negative. So we have to realize, guys, that there's a -1 here. Oops. Okay, so we're going to go ahead and rewrite this equation to read y equals 1/2 raised to the -1 actually makes 2. And so this is y equals 2 to the t. And 2 is our base, and a base of 2 is actually going to be growth. And so it's not choice 3. Okay, we're going to go ahead and go all the way back to our first choices here, now that we got that common misconception out of the way. And we're going to go ahead and raise 2 to the point, to the 0.3. And so we're basically rewriting this equation to be y equals 2 to the 0.3 in my calculator is 1.231 ... raised to the t. And with a base of that, 1/1, this is also going to be growth, which is not our answer. Okay. So we're going to head to number 2, choice 2, and we're going to go ahead and take a look. We're going to type in 1.2 raised to the 3rd power. And so we're basically rewriting this equation to be y equals 1.2 raised to the 3rd in my calculator is 1.728 raised to the t. And this 1.728 is greater than 1, and so this is also growth. All right, hopefully it's choice 4. So in choice 4, we have to realize we're going to raise 5 to the -1st power. We have to realize that there's a 1 in front of that t. And so we're rewriting this equation to be y equals 5 raised to the -1st in my calculator is 0.2 raised to the t. And there it is. There's our base that is less than 1 but more than 0, and therefore this one is decay. All right, so don't be the one that gets tricked by your base. You always have to make sure that your exponent is just the x or just a t or just whatever variable they're using. Okay. All right, let's try another one. Number 2 says find the percent change to the nearest percent for the function f of x equals 2 in parentheses 1 minus 0.3 raised to the -x. So this one's not really any different. All we have to do is realize that this is our base here. I can tell that all of this is my base since it's grouped in parentheses, and my exponent isn't just an x, it's a -x. And so I have to realize that I'm going to need to raise that base to the -1st power. Okay? And so I'm basically rewriting my equation or my function to be f of x equals 2 in parentheses. Okay? When I type in 1 minus 0.3 in parentheses in my calculator raised to the -1st power, I end up with 1.42857 ... raised to the x. And now I can say that this is my base, which is growth. Not that this question asked, okay? But because it's growth, we're going to go ahead and do what we did on the front side where we take our base and put it equal to 1 plus r because it's growth. We're going to subtract 1 and we end up with a rate of 0.42857. However, we have to still multiply it by 100 or move the decimal 2 places to the right in order to get a percent, like our choices are indicating. And so we end up with 42.857%. And the one that closely approximates that is choice 2, 43%. Okay. Number 3. It says, does the function y equals 4 raised to the negative 2x represent exponential growth or decay? And what is the percent rate of change? So as of right now, some people might say growth, but that's just because they looked at the base. If they look at the exponent, and the exponent is not just an x, we have to realize that we're going to really need to type in 4 to the negative second and rewrite this equation. So we're going to keep the y equals in our calculator. 4 to the negative second is 0.0625 raised to the x. And now that the exponent is just the x, we can go ahead and look at our base and say, hey, less than 1, greater than 0, this is decay. And that was the first question that they asked. Because it's decay, we're going to go ahead and take that decimal of 0.0625 and put it equal to 1 minus r. We're going to subtract 1 and divide by negative 1 so that we get an r value equal to 0.9375. We're either going to multiply by 100 or move the decimal place over 2 places to the right to turn it into a percent of 93.75%. And there's our percent rate of change. Number 4. Number 4 says cobalt has a half-life of 5.2714 years. That means half of it will decay in that amount of time. Therefore, the amount of cobalt left after T years can be modeled by this function. And you guys can see that this is the half-life formula. Okay? We use A of T, they used N of T, no big deal. We use A sub 0 and they use N sub 0 to represent the initial amount of the cobalt. 1/2 is in parentheses because it's a decay. Half of it decays or decreases, or 50% goes away. Okay? Every 5.2714 years. All right? And so they want to know the amount of cobalt in the sample is decreasing at approximately what rate each year. So all we have to do is realize that we want to take our base and raise it to our exponent, but you do have to realize there has to be a 1 on top. And so that we're going to type in 1/2 in our calculator, raised to the 1 divided by 5.2714. And so again, we're basically just rewriting our equation that they gave us so that the exponent is just the t. Okay? And when we type in 1/2 raised to the 1 divided by 5.2714, we end up with 0.876786 ... raised to the t. And now we could go ahead and say, yes, this is definitely decay, which we knew it was going to be because it was half-life question. Okay? And because it's decay, we're going to go ahead and take our decimal and put it equal to 1 minus r. We're going to subtract 1 and divide by negative 1 in order to get an r value of 0.123213 ... We're going to multiply by 100 or move the decimal so that it's 12.3213%. And so that is closest to choice. Be careful. That 3 is not going to round the 12, so we're going to say 12%, which is choice 2. All right, guys, last question, number 5. It says that the function P of T equals 43,000 e to the negative 0.025 t models the population of a city in hundreds T years after 2010. At what rate is the population changing? So they want to know the rate. And we can tell them, as long as we know that we have to take our base, which is e, and raise it to the negative 0.025. And again, we're essentially just rewriting this equation so that the exponent is just the variable. Okay? And so this is 43,000. E to the negative 0.025 goes into my calculator and ends up giving me 0.975309 ... raised to the t. And now that that exponent is just all by itself, we can go ahead and say that this is below 1, which is decay. And so we're going to go ahead and get rid of choice 1 and choice 2 because they say increasing. And we are definitely having a decrease here, okay, or a decay. Because it's decay, we're going to take our decimal, 0.975309, and we're going to put it equal to 1 minus r because it's decay. We're going to subtract 1, and we're going to divide by -1, and our rate comes out to be 0.02469 ... Remove the decimal over 2 places to the right to change it into a percent, and we have 2.469 ... percent. Okay, and so we're decreasing by about 2.5% each year, which is choice 3. Okay, all right, guys. Hopefully that helps on telling whether something is decay or growth. And you now know not to just look at the base, but you also have to look at the exponent on the base. And if that exponent is anything more than just the variable alone itself, okay, we have to make sure that we type in that exponent on that base in order to get that variable by itself. All right, guys, I'll see you on the next day notes.